Is good? All right, I'll begin. Dear Father, we thank you for this day. Again, Lord, I thank you for these students. Just ask you to bless our work today, Lord. In your name I pray. Amen. Oh. Did any of you get a chance to do Top Hat weekends? Yes. Was it exciting? It was so valuable tonight. Right? I told I'm gonna.
I will say we have text record of Bethany saying how exciting. So
I think she did say it.
I'm gonna roll it out for linear algebra this weekend. I'm not sure. Okay. Huh. I'm going to roll it out for linear algebra this weekend, I think. I'm not sure that they're sophisticated enough to appreciate Top Hat weekends. But I have to try to help them mature as possible math majors. And
you should have seen the excitement that was filled in my 422 class.
That's right. So, since we're discussing this vile thing, 5590. 5590. So guys, obviously I will, high on my list of things to do is to write your solution. Now, I have given you a solution to problem 77 already, right? And a couple of things in here. But I think it'd be healthy for us to go through maybe problem 84. Let's see if we can solve this one together. Yeah? Well, what do you want to talk about?
I don't know. I just don't know what's happening.
In what sense you don't know what's happening?
Every sense.
So you want me to talk generically about what you're confused about with tensors?
I want you to recap what I'm supposed to know.
Recap what you're supposed to know about tensors. Okay, I will take that under advisement. Let's see here. We've got D plus 3A plus 2B. Any other requests? Let's see here, 2C.
Okay.
Exact sequences I will not try to talk about today. Now, That's right.
Something I should worry about.
Well, it is probably something you should worry about because it's on my list of things to understand today, which means that it's, if it's something I'm currently confused about, that means I'm going to investigate it and figure it out. That means it's on my mind, so connect the dots. Yes? Right? Yeah. I mean, it's not that mysterious how I operate, I get thinking about something, that something tends to be on the test, But anyway, one of the things I would say, Liam, is that the definition that's given for split in Rotman is not the usual definition. The usual definition is the proposition which follows the definition that about the direct sum. Like that, when I started Googling these things in my spare time today, everybody was taking that proposition as the definition. So it seems to me that staring at that proposition might reveal a solution to me, because it will reveal the sort of structure that what it means for it to be split. That's my hope. Anyway, okay, so this one here. Let's see if we can't uncover what this is isomorphic to as a, finitely generated abelian group. So I think the first order of business is to write down the relations matrix, right? Why did I put D first in all these?
It makes life easy.
It makes the Smith form reduction.
I should stick with D being the first thing?
Because all the ones.
Okay. I think the reason I put the D there to start with was so that you'd write down the ABCD matrix and then go, look, we can swap the first and the fourth columns, but you already swapped columns 4 and 1 by relabeling the generators in the order D, A, B, C. So you beat me to it. Good for you. Let's see here. So, uno, tres, dos, dos. Let's see here. Un. Oh man, this is not a good day. Which one was I on?
You were on the second one.
I think I combined the. I think I'm starting to combine them, aren't I?
0 in the second column.
Oh, right. Because A is,
Oh, yeah.
A is 0.
My bad. Let's see here. Let's see here. 1, 6, 4, 4. All right. So next order of business would be to do what?
Row 2 minus row 1.
Mm-hmm.
And row 3 minus row 1.
Fine, I'll write them out. So you said row 2 minus row 1 and row 3 minus row 1. Okay. So what that means is we're just combining the relations, right? We're just adding the relations to make new relations. We aren't redefining generators with that, yeah.
So for the one with the knot, there was a column of zeros on the end. Why is that different?
You could put a column of zeros here.
Okay, but for the one with the knot, then you said the 2 columns of zeros were free, so then you like added it in C.
Oh, I did? Oh.
I think
But I think the
there were
original,
more variables.
there were more variables at the outset. There were 5 because there were, or 6.
But we did start with a column of zeros.
We might have, but that was just coincidental to the setup of the crossing equations.
Okay, but then like at the end there were 2 columns of zeros, so one makes sense that would be like a free variable. But
No,
then
but I don't think that I wrote down a column of 0. I shouldn't have written down a column of zeros for like an inhomogeneous column, did I? Oh, no, I shouldn't do that. I don't think I should do that. That was not done in that PDF I posted for you guys, right? Have you looked? Have you had a chance to remember?
So if
I
you
don't
left
think
with
so.
a 1 at the end, then that would be just C? Or
I mean, I guess you could always, it's somewhat, I think this is sort of analogous to when you're solving a homogeneous system, do you have to put the column of zeros at the end or not, you know? I mean, you could, as long as you remember the interpretation, right? You can't shift back and forth between this matrix being just the coefficient matrix and this matrix being the augmented coefficient matrix. We need to stick with one throughout a calculation, but a given calculation, you could always write more zeros. If I wrote more zeros than I needed to the other day, I'm sorry, I didn't. Okay, so what's next? And I won't even, you know, next up, we just clear out the top column, right? And that does not affect the lower right block here, right? Now, if we were being, and again, I promised you guys I wouldn't test on this aspect of it, but this is what? This is C2 minus C1, C3 minus C1, C4 minus C1, right? And all of those would go into figuring out, if you wanted to figure out what the isomorphism is, the explicit, the explicit mapping of generators to generators, what A becomes in the new basis, then you need to keep track of these and sort through it, right? Again, I'm not testing that on the in-class test, but that that should be noted. Like the column operation corresponds to changing your set of generators. Here, the initial set of generators is, well, according to you guys, DABC, right? Because you, great. All right. Anyway, so now we have done what we can with the first position. Now we focus our attention on these guys. The algorithm says we look at the greatest common divisor of those, and we're going to aim to making the top upper left to that, whatever that is. 8 and 3 are relatively prime, so the GCD is 1. And relative primeness is always judged with respect to the ring over which we're working. All right? So here we're working over a Z module. This is a Z module. So it's just the ordinary notion of primeness. I mean, relatively prime in GCD. But let's see here. What are you going to do? I think I'm going to do row 2, row 3 plus row 2, yeah? And here's where you got to be careful. At times in my careless past, even more careless past, let's say, mathematically speaking, I have at times thought, oh, I can divide by 3 here. And if you could do that, I think it always just, if you could divide by 3, I think you could always just make it ones down the diagonal. So like, this is not allowed. We can only rescale by units here, which are 1 and minus 1, but row addition, of course, is allowed. So I got 2 and 10, yeah? All right. And then, it may not be obvious, but because 3 and 8 are relatively prime, that means that there is some way of adding 3 to 8 to make it go away. I mean, or I should say, make it go back to 1, right? I mean, I don't know. Let's see here. I don't know, there's various ways to go from here. What I'm going to do, just because it pops out at me at the moment, is I'm going to say column 4 plus 3 times column 2. And that might not be what you do, and that's okay. That puts a minus 1 here, right? So then my next move is going to be the column swap. Move that 1 over. And so maybe if you're smarter than me, you would have created the 1 here to start with so you didn't have to swap, you know? So column swapping gives me what? 1, 0, 0, 0, 0, minus 1, 0, minus 3, 10, 0, 10, 2, 0. Tell me if I did it wrong, I can't. All right, and then next move, I will add row 3 plus 10 row 2. Minus 30, I guess. Is that right?
Can't you just get rid of the 10 by subtracting 5 and column 3 and column 4?
5?
Well, oh, now it's 2. Like column 2 minus 3, 5, column 3.
In the red matrix.
Oh, so you want to use this to kill that? Sure, you could. Yeah, yeah. I'm a slave to my algorithm, I guess. You know, I keep doing this thing where I clear out below and then I clear to the side. You know. But you're right. Let's be lazier. So your point is that I could do column 2 minus 5 times column 3, right? Actually, so that's the way you did it in your homework? Let's do it another way. Make sure we get the same thing. I'm going to stick with what I did. What did I do? Row 3, minus 10, row 2. All right. Then I can clear out the 3. And change that 1 to a minus 1 by multiplying. What's wrong with me? 0, 0, 2. Good grief. Do you agree? I mean, I use the minus 1 to clear out the minus 3, and then I multiply by minus 1, as is my right, because that's a unit in z. And then I'll use that 2 to clear out the 30. Column 4 plus 15, column 3. And there we go, Smith normal form. So I hope we agree on the same Smith normal form. Do we? You also get 1, 1, 2? Like that? Did you get that? Okay, okay. So this means that, there's a new set of generators, right? There's a new set of generators, let's say D prime, A prime, D prime, A prime, B prime, C prime. And the relations that they're subject to are kind of, like D prime is equal to 0, A prime equal to 0, and 2B prime equal to 0, C prime free. So up to isomorphism, we see that G is isomorphic to Z mod 2Z. Well, excuse me, let me write it as Z cross Z mod 2Z. Now the what's that? And while we're on the topic, A1 is 1, A2 is 1, A3 is 2, right? So the sort of our more general theorem says that G is isomorphic to what? The R module, which this is a Z module, right? So Z mod A1 direct sum Z mod A2 direct sum Z mod A3, and I forgot the free piece, right? But the thing is, the A1 and A2, well, one is, this is Z, right? So like these two copies in the middle, this is just 0 plus 0, so we just drop that, and what we're left with is Z. You could write cross, you could write direct sum, it's up to you. There's no real distinction between those here. They're competing notations for the same idea in this context. Es bueno? Yeah.
You're using so in G isomorphic to Z prime, the rest. You're using the parentheses like A1 parentheses A2 as generators of A1?
Right.
You're using that the same way that you use like Langle-Ringle?
Yes. A parentheses A is Langle-Ringle A. Yes. Yeah. And you notice in Rotman, he also has the Lingle-Lingle, the Wrangle-Wringle, which has a specific meaning relative to the FX module structure. But okay, anyway. So you guys had so this is good? All right. I thought it would be productive for me to go through the, make problem 89, maybe problem 88. I know you guys want me to talk about tensors. I'm not sure if I can say much there. I mean, the main thing is, if we have an R module M, we have an R module N. Both of these R modules, well, are bimodules. In other words, they allow multiplication on the left and the right by R. That was sort of the end game of that tensor section. That's where we want to live, is like the greediest, most nice, common kind of tensor, which is this. For example, vector spaces have a natural like bimodule structure. You can multiply scalars on the left or the right. And the rule to connect the two is just C times V is equal to V times C. Right, so we could, whatever. But if this is an R bimodule, then, you know, note M and N are Z modules, yeah? So M cross N is Z module with respect to the usual product of modules, right? In fact, it's a Z bimodule. I mean, frankly, it's an R bimodule. But anyway, yeah, in fact, it's an R bimodule. Sorry, I think I'm juxtaposing the more abstract start of the section with the more specialized end of that section at the moment. I probably should just say M cross N is an R module, yeah? I'm trying to remember. Well, let me just stick with it. Maybe it'll come back to me as I'm doing this. So this is an this is a Z module, and then essentially we just do M cross N quotient, some ideal of tensor relations, right? And that is defines M tensor N. And what you really need to know in terms of basic calculations is those relations, right? Because those tell us how we can calculate on the tensor product. What are the relations? Let's say we have A tensor B plus C, or we have A plus B tensor C. Can you simplify those? What if we have RA tensor B versus, you know, A tensor RB? Can you, are these equal? Yes, they're equal. Okay. And then, of course, above we can. Then I would say the other main thing that we should all know about the tensor is the relation between the tensor and the multilinear maps, right? So like what's, yeah.
Should that be A tensor C plus B tensor C?
Did I do that again? Oh yes, I did that on the linear test this morning. So fortunately Dylan noticed early on. Wouldn't want to make them prove a wrong distributive law for matrix multiplication. That'd be bad. No, I did not.
You did not?
I did not, because you guys just memorized that.
Well, yes. No, we understood it, Morgan.
I am quite certain that I gave full credit on the sock shoes problem last year to many people who did not show understanding of said concepts in other contexts, which says to me, I have been asking the question so long people are memorizing it, which means it's no longer a useful question.
Did you ask them about the CCP?
I did not, but it was on the test. I asked them to prove.
In the library, I was asked about this yesterday.
I asked them to prove this.
It was that one.
Ah, Good choice. That is what I asked them to prove. Because it's got matrix addition. It's got matrix multiplication. You know, it's got all, and you really have no prayer of doing that unless you understand index notation. That's what I'm looking for in this problem. So, wasn't bad. So the other thing was, guys, the interplay between the tensor product and bilinear maps. We saw that that was used. Remember that day I did specific examples about, you know, what is this tensor that? And one of the ways we proved something exists was to just exhibit the bilinear map on the Cartesian product of the things. Go back to that day. You'll see that that interplay between bilinear maps and the tensor product is kind of an important calculational bit for actually doing, if you want to, you know, recapture the examples we did in class there. And you know, then there's deeper things, like it's useful to know the theorem if you have two vector spaces, right? If you have two vector spaces, let's say V and W, you know, and V is the span of beta 1 and W is the span of beta 2, say over the same, well, let's say over the same field, yeah? Then we have a theorem that V tensor W has basis what? We could do something like VI tensor WJ such that VI is in beta 1 and WJ is in beta 2. So the dimension of the tensor product of two vector spaces is multiplicative. It's like the dimension of V times the dimension of W. It's that big. Now, where did this matter, knowing that that's a basis? That can be very helpful if you're proving something specific about whether or not something could be a simple tensor, right? There's a homework problem where to prove that something was a simple tensor, it was useful to know that E1 tensor E2, E1, 2 tensor E1, E1 tensor E1, E2 tensor E2 formed a basis for the two-dimensional vector space tensor with itself. And we were able to use that to show that the given vector couldn't be simple. I talked about this to you, Bethany. I can't remember what problem that was. 71. Problem 71 or 72. So sorry, I haven't written the solution down except for bits of it for you, Bethany, but on that day. So it seems to me that that's a useful result for that kind of problem. I would say that's the other thing is what's a simple tensor, right? Simple tensor means that, like, you know, V tensor W is simple if V and W are vectors, right? But versus, say, V1 tensor W1 plus V2 tensor W2, this would not be simple. And you might wonder, does there exist an A and a B such that, you know, does there exist A and B in the space such that can be rewritten as a single tensor, right? It may or may not be the case that you can do that. If you can do that, it's a simple tensor. If you can't, it's not. That's just an interesting question because it gives us something to cut our teeth against the using the relations on the tensor product. That's pretty much the reason we're looking at it, is just to get better at the relations. That's pretty much it. There is, of course, more to learn, but I think that would be my 2 cents for today. Let's look at problem 88, see if we can sort through that right quick. I think we can. What do you guys think of this one?
I spent many hours doing it the wrong way and then realized I had to do it in about 5 minutes.
Ooh. That's good. At least you got to the right point. Let's see here. All right, so that is actually a specific matrix. That means 2. And I'm sorry for those of you who are not in my linear. You know, if you were lost on what on earth this thing was, you could have asked me. I would have told you. That's it. That's what that means.
I
So you-
said in our group message,
some-
I think not having cooked for linear is really biting me in the butt with this one.
Yes, that is accurate.
What?
You weren't in that class?
I had some more simple. Yeah, we did one group the entire semester. I don't know about any of these groups that I'm talking about. They were all calculations.
So that's part of the reason I wanted to cover this in here is because I don't think it is covered much in the other 321. And this is actually kind of baseline stuff to know for grad school. Like the Jordan form is important. But there it is. And I asked you to look at the square of it. So this you can straight up square is the thing, right? What is m squared equal to?
It's like 4's on the diagonal.
Uh-huh. And?
And then was it 4's on the super diagonal and then a 1 at the top?
See, the lazier way to do this would be that this is 2 times the identity plus n2. So if we square that, we get 4i plus 4n2 plus n2 squared. And so the answer, you're going to have 4's here, and you're going to have a 1 up here. Am I right? See, n2 squared, n2 is the nilpotent matrix. Well, you could call it n3, whatever you want to call this thing. It's this guy. And the thing is, when you square that, you get this one. This is part of the driving matrix algebra behind the Jordan form, like this pattern. All right, so with this, it's actually not too hard to construct a Jordan basis for this. Like, I can tell you already, if I think about this thing being A, okay? A, okay. Sorry, I'm an idiot. A times E1 is equal to 4E1, so it looks like E1 is an eigenvector. Yeah?
It looks like what's
E1? Like 1, 0, 0?
Yes, it was.
It's right here, right? Yeah. And then I want A minus 4i times some vector, let's say V2 equal to E1. This is the two-chain condition. Well, the generalized eigenvector of order 2 would solve that equation, right? But that is what? That is 0, 4, 1, 0, 0, 4, 0, 0, 0 times V2 equal to 1, 0, 0. Can you tell me what a solution is to that? I'm doing this the wrong way, guys. I'm sorry. Let me behave. We should find the thing that we should look at A minus 4i, and that's what? This, right? And if we square that, what do we get? Is it 16, 0, 0, 16? Okay, so what would a generalized eigenvector of order 3 be? Apparently, I mean, okay, so I'm not verbalizing my thoughts well enough here. Once I find m squared, it's clear to me that the eigenvalues are 4, 4, and 4. And I also have been at this long enough to realize that that is going to, there's an algebraic multiplicity of 1. There's going to be, there's an algebraic multiplicity of 3. There's a geometric multiplicity of 1. Like, I know once I see that, actually, that after I get through the static here, the Jordan form of m squared is going to be J34. It's going to be J34. So then my goal is, with that intuition, is to try to find a 3-chain of eigenvalue 4. So to do that, one way is to find my generalized eigenvector of order 3. If I can find that, then I can power it to get the rest. Like, let me show you what I mean. So this tells me actually what it should be. Because a generalized eigenvector of order 3 should be what? It should be something that a minus 4i squared, right, on V3 is not equal to 0, yet a minus 4i cubed on V3 is equal to 0. Of course, a minus 4i cubed here is stupid because it's just 0. So that won't give you any insight at all. You got to look at the one less than that, the square. So can you tell me what my choice should be, given that 16 there? Where it is? What's my V3 got to be? I heard a 004. 004. I take your 004 and I trade you a 001. But anything would work. Any scalar multiple of that will do.
Where is that coming from?
That is not in the kernel of this map. I just see, when I multiply this times that, I get non-zero. So that is a generalized eigenvector of order 3 with eigenvalue 4. And once I know that, I can create the other ones by multiplication by a minus I. So like a minus 4i rather. A minus 4i v3 is what? I get un, quattro, 0. Look at that. That is my v2. That will be a generalized eigenvector of order 2. I know it's not an eigenvector because when I multiply a minus 4i times that vector, I get something non-zero because of the way it was constructed. Anyway, that's my v2. And then v1, take a minus 4i times v2 and set that to be v1. This is not how I taught you guys to do stuff in linear. How do we do it in linear? Looks like I get a 16, and then a 0, then a 0. So if you guys believe me, and I would describe this calculation as top-down. I found my generalized eigenvector of highest weight possible. Here, 3. Once I have that, it generates a chain below it by multiplication by a minus lambda I. So we had our v3 multiplied by a minus 4i. That gives me v2 multiplied by a minus 4i. That gives me v1. If I multiply by a minus 4i again one more time, I get 0. In other words, what I'm trying to get at here, guys, is 16, 0, 0. 1, 4, 0. And what was my initial one? Since I did not take your advice, I mean, I put a 1 there. This is a generalized eigenbasis. And I think I put it in the right order, right? I put the eigenvector first, the generalized eigenvector second, and the highest generalized eigenvector third. If I do the t-cyclic basis stuff, though, it inverts, right? Like, take the highest weight thing and powers of that generate, but it actually kind of, the way I've got it, see, I go from here to here by t minus 4i. I go from here to here by t minus 4i. Anyway, my point to you guys is just this, is that this beta means that the, if I do beta inverse m, what would I call it, m squared? Oh, a, I guess I called it a. This, well, then what I'm going to get is the 3 block with eigenvalue 4. So anyway, all this just to tell you what we guessed, what I guessed a little bit ago. So if I had to guess, Bethany, the way you did it was to find the eigenvectors for m squared. Did you find the eigenvector first and then the generalized eigenvector?
Yeah.
Oh, something else entirely.
Yeah.
Tell me more.
Okay. What we did is found the characteristic polynomials.
Uh-huh.
Because you could just do the determinant of, because it's like upper triangular, right?
Right.
So it's x minus 4 cubed.
Right.
And then I just showed that that had to be the minimal polynomial also.
Okay. Oh, hey, that's not a bad solution at all. So you said the characteristic polynomial of A is x minus 4 cubed. And you gave arguments that the minimal polynomial of A was also x minus 4 cubed. And so that implies, what does that imply? That implies that the elementary divisors are a kind of sad list, right? It's a list of 1. Look, the elementary divisor. It's just that, right? Which means then, by our correspondence theorem, that it's the Jordan 4 block, J34. I would be delighted with that argument on the test if this was a question. That's totally within ballpark. So I'm just showing you a much more concrete, direct assault on the problem. So to find the Jordan form, we have to find a Jordan basis, or argue through other theoretical means it has a certain format, right? So you tell me, the problem, I think problem 89, what do you think? I mean, I think 89 we have to do with direct calculation, right? So I think problem 89, the way to do it is actually to try to exhibit a Jordan basis. Yeah? And I would point out here that breaking out like choosing a basis and writing out 4x4 matrices is needless here. You can instead just look at it directly. So the linear transformation is the double derivative, right? And I said I recommend calculating the matrix of T with respect to that particular basis. I'll tell you what I'm going to do. If we look at, let's just look at the monomial basis. What happens with T1? It's 0, right? What's T of x? It's 0, right? If we take 2 derivatives of x, we get 0. What's T of x squared? 2, which I would say is 2 times 1. I don't know if that's helpful or not, but there you go. What's T of x cubed? Yeah, 6x, right? And I said that this is for f of x in possibly degenerate third-order polynomials, right? P3R. Find the Jordan form. So again, what I want to do is I want to find, I think there's two chains here, all right? And I want to find the generalized eigenvectors. So like, what if I do t of 1/2 x squared? What's that give me? Gives me 1, right? And that gives me x, right? And on the other hand, what else do we know? Well, we know that t of 1 is 0, and we know that t of x is 0. So what this means is we could look at, say, beta 1 as 1 comma 1/2 x squared, and then beta 2 as x comma 1/6 x cubed, and those will each be a chain basis with eigenvalue what? Did somebody say 0? Okay. In other words, so the matrix of T with respect to beta is going to look like 0, 1, 0, 0, whoop, 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 0, 1, 0, 0. And that is the 2 Jordan block with eigenvalue 0, direct sum with the 2 Jordan block with eigenvalue 0. That's the Jordan form of the transformation. Yep.
Why is it 0? I said that, but I don't really understand why.
Ah, because this is t minus 0 times the identity acting on 1 equal to 0. Or if you like, this is t of 1 equals to lambda times 1 equal to yeah. The eigenvectors have eigenvalue 0 here. There's probably some fantastically lazier way to do problem 88 than the way we did it. But anyway, those are just some thoughts. Now, to be clear, guys, in problem 87, I said find both the rational canonical form and the P which similarity transforms to A. Like finding the P which similarity transforms to A, that is not a reasonable test question. Finding Jordan form, finding rational canonical form, calculating Smith normal form, fine. All fine, well and good. Finding the P which similarity transforms, that is a graduate question. Yes?
So we got the same answer using the characteristic polynomial again.
Uh-huh.
So that's cool, right?
You mean you got that the eigenvalue was 0, 4p-ed, and then you figured out the minimal polynomial was?
Well, yeah, so we found out basically that, E1 is, you find the T basis or whatever for the basis that you gave us, like x cubed, x squared, x1. And
Well,
with the transformation, that's like, zeros on the top 2 rows, and then I think a 6 and a 2 somewhere in there.
uh-huh.
And then basically you can you do the same thing that we did last time, like x minus xi minus that matrix, and then you just have x's along the determinant of that is once again x to the 4th, but this time x squared is the minimum polynomial, and it's just 2 of x squared.
Yeah, so if you have some way of seeing that the minimum polynomial is x squared, I'm all with you. The question is how you did that.
Because so in the book, it kind of goes back and forth in between using polynomials and using like the matrix. And so like, it'll find the characteristic polynomial, and then it'll say because the matrix squared, in this case, like if it's x to the fourth, then the eigenvalue is 0. And so the matrix squared is 0.
Like your matrix when you put in like all the zeros and then the 6 and the 2.
And so because it squared is 0, that means that x squared is the minimum polynomial. Because x put into that.
Perfect. If you did that, I'm all with it. I'm all with you. So this is the struggle, right? Do you want to find a basis to see something in? Is that more natural to you, or is finding an argument to show the minimal polynomial is what it is more natural to you? I don't know. It's up to you, right? I mean, for me, sometimes the basis, but maybe I should think more about minimal polynomials because it seems like what you're saying is a much easier calculation, right? I mean, to see that the matrix of T with respect to some basis squared is 0 is not that hard to do, right? It's not hard at all. And once you see that, that proves that the minimal polynomial is x squared because it can't be x because T is not 0, right? Only one transformation has x as its minimal polynomial. It's a very stupid example. It is, you know, what has x as its minimal polynomial? I believe so. What's the minimal polynomial for the identity? Oh, it's x minus 1, right? Yeah. Sorry, I was having an existential crisis there for a second, but I'll get over it. Yeah, so of course, the other game you could play would be to do the Smith normal form thing on this, right? What was your matrix? Since you didn't do my silly basis rescaling, what did you have? Yeah,
Zeros all along the top.
Uh-huh.
And then the second row is null.
Okay.
And then the third element in the first row is 6. Because we're going from x cubed down to 1.
Okay, 6.
So 6 and then zeros.
Uh-huh.
And then it was 0, 2, 0, 0, 0.
Ah. So if we do x minus this puts a minus here, this puts a minus here, and we put x's here, right? And so like we could play the Smith normal form game and see what happens. I mean, it might be fun. No?
No, because I think,
It doesn't seem fun?
That was how I checked. It wasn't fun.
Oh.
That was how I checked.
Huh. What's the first thing I need to do?
That both invariant factors were x squared rather than having like an xx.
So like I definitely cannot convert that x into a 1. Right, so the first thing you got to do is you got to flip the third row to the top row, right? And then so forth. What should we eventually get to? We should eventually get to un x squared, right? You got to that eventually, right? Yeah. But you also will gleefully admit that it's like it's way, way easier to find the minimal polynomial through direct computation. And the thing is, once you do that, the complete list of invariant factors is already like sitting and staring you in the face, right? Like, so I don't know. There's a lot of ideas that interplay here. What's the right calculation for a given example? It's debatable, you know? But anyway, so I will work on getting that solution written for you guys.